Hello everyone. In today's class, let us start discussion about apparent weight. Okay. So apparent weight means what and how it is measured in different cases, how we calculated. So we will see in deeply. Here is the situation. One example we have taken. When a person just to place one foot on the one leg on the weighing machine, it is giving some reading, and the same person standing completely on the weighing machine, the reading is some different. Okay. So actually we need to start here. Weight of a body is nearly constant near the earth surface. Generally weight of the body is given by W equal to mg. Okay. So generally on the surface of earth, W equal to mg should be same for given mass. Okay na? So now what here mass of the person constant and on the same level of the surface g value constant. So mg should also remain constant. But in the scenario, whatever the diagram we have seen, means in the figure we have seen, that is giving different. So you might get the concept also, sir, here not complete weight of the body given by the weighing machine. Here complete weight of the body given. Okay. But every time complete weight instead of that, what we can find out here, that explanation will be given in the last point. Weighing machine measures the contact force exerted. So how much force we act on the weighing machine? Okay na, that is example you can say the person is exerting some force. Okay na, single leg and exerting force on the weighing machine downward. The same will be means shown by the reading, that is actually indicated with N, called reaction. Okay na. So here that is actually we can call normal reaction. So in this second case also, okay na, complete contact force, how much person exert on the weighing machine, the same contact force shown by the weighing machine in the terms of reading. So this whatever the contact force or normal reaction or reaction force shown by the weighing machine is nothing but our topic, today's topic, that is apparent weight. Okay na. So whatever this reading is given here, that can be written as apparent weight, right? So this normal reaction is measured by the weighing machine, we can say, and that normal reaction only we can call in detail apparent weight. Okay na? So now let us move on to next slide. But what about the person in the lift, which means whenever person is inside the lift and weighing machine is taken along with him, and whatever the readings given by the weighing machine we will observe in this case. Okay na? So that is how we will write the equations. Here it is given. We will learn about the concept in coming slide. Here lift is there and lift is moving upward with acceleration, and the person weight will be not equal to mg. This is, there is some value changes, and how it is going to change, let us observe first of all in the coming slide. So change in normal reaction are nothing but we can call change in weight, that is apparent weight we need to measure. Okay. So here first case we can discuss, this is the case 1 actually. Okay. So now what happened, the lift is moving upward with an acceleration A. Here weighing machine kept inside the lift, and whatever the mass m is kept on the weighing machine, and actually if acceleration of this lift is 0, then directly normal reaction is written as mg. Okay. But here lift is moving upward with some acceleration. In such case, what is the reading given by the weighing balance? Here weighing balance is showing that what m into g plus a. That answer how we can derive? Let us start about the discussion. Okay. So now this is the mass free body diagram. Now coming to the point, mg acts vertically downward. Okay na. Now n acts vertically upward. And here acceleration they have taken downward. Actually acceleration is upward, but The person inside the lift is in which frame he will come? Non-inertial frame he will come. Okay, na? So in non-inertial frame means there is a pseudo force exist. So that's what, yes, this is what actually pseudo acceleration, and we can say downward pseudo force is going to act. The pseudo force value is exactly equal to mass times acceleration of reference frame. Okay, so that's what we can write down here. Total upward force equal to total downward force, and n equals to mg plus ma, m taken common into g plus a. Okay, this is with help of what general case, what we can write pseudo force with the help. And if we do not know or do not aware about the pseudo force, then how can we derive the same equation? Let us start discuss the same concept without help of a pseudo force. Normal force upward only, downward mg only, and it is accelerating upward. Okay, na? So just we can write down net force equation. So n minus mg, n minus mg equal to ma. So then we can write down n equal to mg plus ma, where m into g plus a. This is the normal reaction, or we can say weight shown by the weighing machine in case of accelerated frame. Suppose acceleration of the lift is 0, then whenever it is at rest, normal force 1, we can take mg. That is actually, we can see, suppose a block mass m and its weight is mg, then same reading only given whenever lift is at rest. But whenever lift is moving upward with acceleration, what we can say, it gives some different reading, that is n equal to m into g plus a. So we can write down the same answer here. I am writing this answer, that is n2 equal to m into g plus a. Acceleration, if a least value, if you consider 1, okay, na? Even acceleration least value, the n2 value is greater than n1, right? So weight of the block is shown somewhat excess value whenever it is accelerating upward. You need to get this concept here. Means the weight of the block or weight of the particle is appear to be increased whenever it is moving upward direction with some acceleration. So this is the concept we can write down. Okay, the same answer will again come, instead of it is going upward, it is going downward also, but retarding, we should mention. Okay, na? That is what, whenever it is going downward with retardation, then also answer will be same. How like it is? Let us see here. We will observe that concept again. Okay. See, if it is retarding downward with the same acceleration, but retardation indicates what? Minus a, negative acceleration it says. So we will write down it is a downward. Okay, na? So that is minus acceleration, right? So then what we can take? Minus acceleration downward, right? So we can write down here retardation downward is there given, na? So we can write down in this case n is upward and mg is downward. So we can write mg is greater, mg minus n equals to minus ma. We need to write down like this. So minus ma should bring on the left side. So it will become plus mg plus ma. On shifting normal right side, it become positive. That is n equals to m into g plus a. Again the answer is same, which means the same answer we get in the scenario of what? Lift is accelerating upward, okay, and retarding downward. So acceleration magnitude and retardation magnitude same in this case, then normal force or apparent weight shown by the weighing balance also same. Okay, na? So this is what we can discuss in the first case. So now let us consider here how much fraction of weight force increased, that is when it is accelerated and when it is at rest. We need to find out the fractional change. That is, Suppose you can take this is n2, and whenever acceleration of the lift is 0, then n1 equal to how much we can take mg, because acceleration is 0. So, in such case n1 we can find. So, generally n2 is greater than n1 only we can write down. So, what fractional change we can find? That is n2 minus n1 by n1 into 100 we can solve. n2 value mg plus ma minus mg by mg into 100. Here minus mg plus mg cancel, cancel, that is a by g into 100. This is the fractional change in the weight of the block or particle whenever it is at rest, whenever it is moving with some acceleration, upward, retardation, downward. Okay, na? So, this is the concept we can follow for the case 1. And let us move on to case 2. Let us start discuss about case 2 here. Now, this is case 2. Okay. Here same weighing machine is there in the lift and it is moving downward with acceleration a. Okay. Then weighing machine shown some reading that is not actually equal to mg. So, that is here free body diagram we will find out. So, downward force is mg only, n is upward. Whenever it is moving downward with acceleration, then it felt pseudo force opposite to acceleration. That is what we can see. This A is upward and due to this one pseudo force is acts upward. Okay, na? So, then what is the total force upward equal to total force downward we will make. So, n plus ma equal to mg, and ma shifting on right side become minus, n equal to m into g minus a. So, this is the normal reaction shown or reaction force shown by the weighing machine, and actually whenever acceleration is 0, then we can see n1 equal to mg, and here n2 equal to m into we get what g minus a. So, definitely n1 greater than n2. Okay, na? So, n1 value comes out to be somewhat increased as compared to whenever it is at rest. Okay. So, sorry, as compared to whenever it is accelerated downward direction, right. So, n1 value greater than n2. So, now here the scenario whenever it is accelerating downward we got, and same case whenever it is retarded upward direction, means it is moving upward with retardation, same value a, then also we get the same answer we have seen in the last case. Okay, na? So, we will take the help of the same kind of condition. Here see, this is m and downward mg, upward what normal reaction, okay, and it is moving downward with acceleration a. Suppose it is moving upward with retardation minus a, okay. So, we will take n minus mg equal to minus ma, n equal to mg minus ma, that is n equals to m into g minus a. The same answer we got as we got in the earlier case. Okay. So, for same situation we can define for two cases. Okay. Whenever it is going downward with acceleration a or moving upward with retardation a. So, we can discuss this one, same answer will come. In both the cases, in these cases moving downward with acceleration or moving upward with the retardation, what is the weight force we got, m into g minus a. Then what fractional change in the weight will be obtained. So, that we can find out here. So, fractional change in the weight, here it is n2, again we can take n2 minus n1 by n1 into 100, n2 value mg, okay, minus ma, minus ma, and here minus mg divided by mg into 100, mg cancel, cancel. So, finally minus a by g into 100. We got here minus, which indicates what a normal reaction or apparent weight in this case decreases as compared to whenever it is at rest. Okay, na? So, this is the scenario and this is the case we have studied when lift is moving upward acceleration or downward retardation, and second case when lift is moving downward acceleration moving upward with the retardation. Okay, na? And the same situation instead of acceleration, if it is going upward with velocity v, downward with velocity v, constant velocity means acceleration equal to what? 0. Then whenever it is going upward with constant velocity, downward with constant velocity, in both the scenario, the weight force or reaction force shown by the weighing machine is mg only, because acceleration term 0. So, n equal to we get mg. Okay, na? So, this is the condition we can discuss. So, you can take here n equal to, that is mg minus a, acceleration 0, and then we can get what? Mg. Okay, na? Whenever it is moving with constant velocity, then we can conclude one thing. Whenever it is moving with constant velocity upward or downward, and whenever it is at rest, the reaction force shown by the weighing machine equal to mg, and reaction force will be differs whenever it is accelerated upward or downward. That values we have seen. Okay. So, let us move on to next slide. Tension in the cable of a lift or just elevator we can discuss. Okay, na? So, here also we can find out the same cases better. So, first case 1, okay, na? The lift is moving upward with some acceleration a. So, we can consider this is entire box is lift. Just you can consider this entire box is lift, and here tension in the cable whichever holding the complete lift, and total mass of the lift including passengers, including persons in the lift, okay, that is m, and total weight force will be g, mg. So, total weight force mg downward. Now, it is moving upward. Now, we have taken acceleration upward. Then tension in the cable is not at all equal to mg. Whenever acceleration is 0, then tension in the cable equal to mg only we can write down. Then it is moving upward with acceleration. So, T minus mg equal to ma. So, T equals to we can write m into g plus a, and here we can see the tension in the cable increases than the original weight whenever it is going upward with some acceleration. So, you might find in the lift notations, it is allowed only 6 persons are this much weight, or it is allowed only 10 persons are this much weight. Okay. The same persons who are going upward in the lift can be increase number whenever it is coming downward. Okay. Suppose 5 members are going upward, that is the maximum load in the lift. Maximum load in the lift means this is the bearable tension here. So, this much tension will be calculated and given by the lift engineer here. Okay, they will indicate over there with the help of cable diameter and lift size and its mechanism. Okay, na? So, that will be indicated on the lift walls. Now, suppose 5 members are going upward, that is the maximum weight can be bearable by the lift. Then while it is coming downward, one more person also included in the lift, then he can also come along with them. So, what happened? Why one person extra will come while moving downward? Only one person less while it is moving upward. Means that measures, the tension measures here apparent weight. Just now we have seen in the last slide, na, mg plus a. Here also tension will be equal to apparent weight only. It is not equal to mg, original weight if it is equal, na. So, then we can increase one more person to be getting to the lift, right. So, here m into g plus a measures in the tension of the cable. So, that is what this is the maximum bearable tension in the lift cable, right. Suppose if the lift is moving downward with the acceleration, suppose in the same case we can see case number 2, and it is moving downward with the same acceleration a. So, then you can find out here total weight including persons in the lift will be and lift mass. total weight will be mg, and this is cable, and through cable tension will be upward, T will be there, and downward it is accelerating. So we can write net force equation mg minus tension equal to ma. T equals to mg minus ma. So here m into g minus a. So this T2, suppose here initial one T1. If you compare both the T1 and T2, T2 will be somehow less value for the same acceleration for the same mass. Okay, na? So here T1 will be greater, means the values T1, T2 will be depends on the direction of motion of the lift. So that's what, while it is going upward, it carries only 5 members maximum suppose, then it is while it is coming down, one person extra will also come, there is a chances. Okay, na? So don't do practically and don't make disturb the lift motion. Okay, na? So this is what actually we need to discuss, how tension is going to alter in the lift cable, right? Now let us move on to next slide. Let us see next question here, that is a lift is going up, means actually lift is going upward here. The total mass of the lift and passengers is 1500 kgs. Okay, na? So here it is given 1500 kgs, the total mass. And next the variation in the speed of lift as shown. Actually here speed changes with respect to time given in the graph. Okay, these are in seconds and it is having a velocity meter per second. So now they are asking the tension in the rope at t equal to 1 second. Okay. So first of all, we need to take the concept here, that is lift moving upward. So tension in the cable we can write T, upward acceleration, whether it is moving upward with acceleration or not, we will find from this graph. Okay. So let us just, I am writing indication, that's it. So downward mg. Let us confirm whether it is acceleration or not. Okay. So 1 second they said, 1 second means this is a duration. So here 0, here somewhere it comes 1 second. Okay, na? So 0 to 1 or 1 to 2, 0 to 2 seconds the line will be inclined at an angle some theta. Means from the kinematics concept we can see slope of velocity versus time or speed versus time gives you what? Acceleration. So definitely acceleration is present here. Okay, na? So acceleration is present for the lift in between 0 to 2 seconds, and the 1 second asked question 1 second. So at 1 second also it is having same acceleration. So that is 0 to 2 seconds the acceleration of lift is constant because slope constant. Okay. So we will find here, that is a slope opposite side by adjacent side. Opposite side length how much? This length 3.6 minus 0. This is 3.6. So this is 3.6 minus 0 by adjacent side 2 minus 0, that is 3.6 by 2, that is 1.8 meter per second square. Okay, na? So now coming to the point, acceleration only and upward only as per the question. So it is also positive acceleration we got. So then T minus mg equal to ma. So this is the condition apt. So T equal to mg plus ma we get, that is m in bracket g plus a. M value how much given? 1500 kg into g value I am taking 10. Okay, na? And a value 1.8. So we can write 1500 into 11.8. So 10 plus 1.8, 11.8. On multiplication it comes approximately 17,700 newtons. Okay, na? So this is the value of tension in the cable of lift. In the same question, if the time duration changed, suppose in between 2 to 10 they asked, okay, slope of this line is how much? 0. Okay, then acceleration also 0. In that case, tension equal to mg. Why? Because acceleration 0 na, so we can write 15,000 newtons. And here we can take this duration, that is 10 to 12 seconds. Here slope will be negative. So in this case acceleration will be negative, that is actually called retardation. So instead of you get m into g plus a, what we get m into g minus a. So g minus a we get here 10 minus 1.8, just we need to simplify to get the answer tension. Okay na? So here different time situations are given in the question, then different tensions will be there because the graph is not same for the different time intervals. Okay. So let us move on to next slide. A mass of 1 kg attached to one end of the string is first lifted up. So here it is a string, okay, it is lifted up with 4.9 meter per second square, which is equal to g by 2, and then lowered with the same acceleration. Here lowered with the same acceleration. Then what is the ratio of tension in the string in two cases? Let us take here mg will be x, here T1 we can write down, so upward na, T1 minus mg equal to mg by 2, because ma we will write T1 equals to mg plus mg by 2, which is m common g plus g by 2, okay, 2 plus 1 3 mg by 2, we get tension 1, right. In this case, so tension will be always away from the point of contact, and T2 I am taking because acceleration is downward. So we will write down here mg downward only, but acceleration downward, so we can write mg minus T2 equal to mg by 2, that is T2 equal to mg minus mg by 2. So we get mg minus mg by 2 is T2 equal to mg by 2. So they are asking ratio T1 by T2. So that is finally T1 upon T2 equals to 3 mg by 2 by mg by 2. mg by 2, mg by 2 cancel, then answer will come 3. Okay na? So this is the way of finding the question, okay, or solving the question in this manner by using apparent weight concept. Let us move on to next slide. Here the apparent weight of man in a lift is W1, that is apparent weight of the man they are giving in the lift W1 when lift moves upward with some acceleration. Suppose the lift is moving upward with some acceleration, so just I am taking as A is the acceleration. So now normal reaction on the person and downward mg. So what do we write now here? N minus mg equal to ma. So just n1 I am writing, so n1 equal to mg plus ma. Here w1 is which one indicates actually n1, because apparent weight na. So this is original weight, n1 is apparent weight. So we will write here w1 and mg I am taking common, so 1 plus a by g, okay na, because cancel. So mg can be taken as a w 1 plus a by g. This is w1 equal to, say this equation number 1. Next w2, whenever it is accelerating downward with the same acceleration. So whenever the lift is moving downward with the same acceleration as the initial one, so its weight is mg, person weight, normal reaction changes. So I am taking as n2. So downward na, so we will write mg minus n2 equal to ma. So that is n2 equal to mg minus ma. N2 value how much as per the question? W2. So I am taking mg common 1 minus a by g, because ma by mg comes, cancel. So mg place I am writing as w, that is original weight of the person. Okay. So this is w2 we got, second equation. What they are asking? True weight of the man and acceleration of the lift. True weight acceleration. True weight means W we have to find out. Okay. So for this purpose we need to take 1 plus 2. Okay na, W1 and here left side W2. Okay, equals to here W 1 plus A by G plus 1 minus A by G, because here also W I have taken common, A by G cancel, so we can get 2W equal to W1 plus W2, W equals to W1 plus W2 by 2. This is the answer for weight of the person. Okay na? So now they are asking acceleration of the lift. So we can just do simplification, that is 1 upon 2. So W1 by W2 equal to W into 1 plus A by G. Here W into 1 minus A by G. W cancel, here G plus A by G. Here it is G minus A by G. G cancel. Now cross multiplying. W1 G minus W1A, W2G plus W2A. Acceleration we want na, so acceleration term we can make one side. W1G minus W2G equal to W1A plus W2A. So that is acceleration equal to W1 minus W2 by W1 plus W2 into G. This is the acceleration value whatever they have asked in the question. Okay. So this is the way we can apply the concept of apparent weight to solve the numericals. Okay, now let us move. Okay, thank you. This is regarding apparent weight.